Hello, my name is Małgorzata O'Reilly. I am an associate professor at the University of Tasmania in mathematics. I am going to talk about stochastic modeling and applications. I'd like to dedicate this little talk to my grandma, who is the mathematician who inspired me. I used to play cards with her. She didn't like losing, so she used to cheat quite often. I heard stories of her sitting on a fence and solving mathematical problems for her neighbors. So I'm pretty sure I got my maths gene from her. Stochastic modeling is one area of my interest. Essentially, what I like to do is, for the fun of that, play with various mathematical objects, especially involving uncertainty, and trying to develop some maths for those objects. So how to compute various quantities of interest, such as, for example, distribution of some process at time t or in the long run. An example is so-called stochastic fluid model. Imagine you have some underlying environment, perhaps modeled by a continuous Markov chain. So there are various states of this environment, for example, weather, that drive the system. So for example, level of water in the reservoir. So you have two variables. One is the phase, which models this underlying environment. And then there is also level, which is some measure, continuous measure of interest that depends on this phase of the underlying environment. And so we end up with this object that we refer to as stochastic fluid model, as it behaves like a fluid. And some years ago, I got interested in this problem of how to compute various metrics for it. And then I had a little breakthrough and developed some methodology. And then, of course, the natural progression is how to make it a little bit more complex. So instead of one level variable, how about we have two level variables, because this could be useful for modeling some real life system. And so two-dimensional or multi-dimensional stochastic fluid models is something that I have been interested and sort of playing with those. And recently I had a little breakthrough and developed some methods for those type of systems that involve matrices. Because of course, the end goal is to be able to compute things, some metrics for some real life problems of interest. So we need to be able to compute things, and so this type of approach is part of so-called matrix-analytic methods, where we don't just develop some lovely pure maths theory, but we also are interested in computing various metrics. A lot of my work involves visualizations and sort of imagining how the systems might evolve. And I guess this is this pure abstract type of fun where I think of how the system is evolving in time. And so, for example, here we have two levels, and this dot in some sort of random manner evolves and moves on the quadrant. And some things that we are interested in, for example, what is this distribution of this two-dimensional fluid model in the long run, or what is its distribution at time t? And you can also consider systems where there's no boundary. And so this is an example of unbounded two-dimensional fluid that evolves in time in this sort of chaotic random way. And what I'd like to know is how to compute the long run distribution of such process and other metrics. And so, for example, I ask questions such as, given some initial distribution of the level, what is its distribution at time t? Or given some initial distribution of the level, how long it takes for the process to reach some level, or in the case of two buffers, so two-dimensional stochastic fluid model, the question might be when the fluid reaches some level in one buffer, what is the distribution if in the other buffer, or what is the distribution of busy period in one buffer, or what is the distribution of the level in one buffer when the other ends its busy period. So these are the type of questions that we like to ask, and because the problem becomes quite complex when we introduce two-dimensional or multi-dimensional stochastic fluid models. This becomes quite challenging, and it's very interesting. And so this is something that I have been studying for some time, and recently I have had a little breakthrough. Here is some example of some computations that I developed for this two-dimensional fluid models. As you can see there in this example, there are 4 different directions that this process can move on a quadrant. And so this is a nice example where there's quite a lot of flexibility in the behavior. And so hopefully this can be used in the applications of some real world problems. And here we see some computations and also some visualizations, some plots of some metrics of interest. And so this is one part of my interest. And of course, although this is pure fun, there are some quite serious applications of this type of system. So for example, telecommunications network, modeling congestion, risk processes, hydropower generation systems, even spread of fire or environmental problems such as coral bleaching, and recently even in vaccine inventory systems. So there's a wide range of applications in various areas, and so being able to solve these abstract stochastic modeling problems it's useful, and it lends itself to various applications in a range of problems that are significant to society. I'd like to mention a couple of applications that I'm also interested in. One is modeling evolution. And so, for example, given some data, some phylogenetic data, I would like to be able to understand the evolution of genes or the evolution of species. And so you can visualize this as a sort of stochastic process where there is duplication of genes, or perhaps